Hey there, folks. Good morning. Let's try another torque problem that's a little more difficult. In this one, we are essentially doing the same kind of thing as we did in the first few problems, which is slowing down a rotating object using friction. In this case, we're designing a frictional brake for a rotating cylinder. We're given the cylinder's diameter, the initial angular speed, and once the brake is engaged, the cylinder rotates just a little over 5 times before coming to a stop. Since we're given the number of rotations before stopping and not the amount of time it takes to stop, we need to approach this one carefully. Let's begin by using the sum of torques equation as our starting point. We saw in the first video of this chapter that an applied force on a rotating object can be broken up into a normal force component and a frictional force component. These two forces have their own torque contributions, which are summed on the left-hand side of this expression. We also saw that since the line of action for the normal force goes through the axis of rotation, the lever arm length for that force is 0, which implies that the torque due to the normal force is also 0. So we can just get rid of that term, and our sum of torques expression is really just one torque that's equal to I alpha. We should break both sides down using their definitions, but there's a problem. We have no idea what alpha is right now. All we have are the number of revolutions before coming to a stop and the initial and final angular speeds. So here's what I'm going to recommend. Let's grab this rotational kinematic equation. Theta F will represent the 5.25 revolutions that the cylinder spins through before stopping. And since we weren't given any initial number of revolutions before we apply the brake, we can set theta initial equal to 0 and just get rid of it. I'm going to call our result here equation 1. Unfortunately, we have two unknowns now. Alpha again, and now time. I know it might seem like we just made the situation worse, but to fix that, we're going to grab another equation, this one. We should use this to get an expression for alpha. Let's set the final angular speed to 0, move the initial one over to the other side, and then divide both sides by time. I'll label this one equation number 2. The plan is to plug equation number 2 back into equation number 1 and eliminate alpha. Then we can focus on the other unknown, which is time. Let's go back to what equation number 1 looked like, and we can insert what we just found. Notice that one factor of time cancels out on the right. And we have similar terms here as well. If you factor out omega initial times t, well, it's pretty clear that we're taking a full amount of that quantity and subtracting half of it, which leaves 1/2 remaining. I'm going to multiply both sides by 2 and divide both sides by omega initial. And now we have time in terms of quantities that we know. We can call this one equation number 3. Remember that we originally went down this whole rabbit hole to try and figure out what alpha is supposed to be. Let's retrace our steps and see if we're any closer to achieving that goal. If we pull up equation number 2 again and plug in equation number 3 for time here in the denominator, and then simplify it, we end up with another expression containing quantities that we know. So we're good. We got alpha now. Let's return to our sum of torques expression. Here's what we had, and I think now is the best time to start breaking it all down using definitions, starting on the left. There's everything that's inside of our torque, and we can go one step further by exchanging the frictional force with its definition as well, like this. Cool. Now the left-hand side is good, and the next is the right. The moment of inertia for a cylinder is going to be the same as the moment of inertia for a disk, which is 1/2 mr squared. And we also have our definition for alpha now. So let's get both of those plugged in over on that side. Now everything is defined, and there's no longer variables that are hiding inside of other terms. We want to solve for the applied normal force here, capital N. But we need to figure out what the lever arm value and the angle between that lever arm and the kinetic friction force are before continuing. And it's not as bad as it sounds. Here's our picture again. Instead of viewing the cylinder from the side like this, I think it would be better if we switched to a frontal kind of face-on perspective. We know that when the brake is engaged, there is a normal force acting perpendicular to the surface and a frictional force acting tangentially to the surface. And let's get this brake mechanism out of the way so it's easier to see these vectors. Let's see, what else? We should fix a few other things as well while we're here. I'm going to erase our diameter and insert the point O to represent the location of our rotational axis. Let's also include a label for the radius, since that's a variable we're actually using in our expression. Now we can move on to the lever arm. Remember, the lever arm is a perpendicular distance drawn from the point of rotation to the force that we're investigating, which I'll represent using this purple length here. There we go. And it is perpendicular to the kinetic friction force as expected. This works out really nicely because our lever arm is actually the same length as the radius of the cylinder. And so with that known, we're actually ready to finish this problem up. Let's go back to our previous expression and start plugging some things in here. I'll switch out lowercase l for the radius, r, and since the lever arm and the frictional force are perpendicular to one another, theta on the left is going to be equal to 90 degrees. Furthermore, the sine of 90 degrees is equal to 1, so we can just chop that chunk off on the left and keep the rest, like this. Next, let's remove the parentheses from everything over on the right and sandwich all those variables into a single ratio, kind of like this. The negatives on both sides can be canceled out, and if we divide both sides by r, as well as mu sub k, well, now we've finally isolated the normal force, and we are at the finish line. But don't get too excited. We still have some unit conversions to do. This involves exchanging revolutions for radians and minutes for seconds. And so here's our numbers with those conversion factors included. Therefore, once we punch this all into a calculator, we find that our final answer is an applied normal force of approximately 7.47 newtons. And that's it. We're all done. Thanks for watching, guys. I hope this helps. Have a good one.